Application of derivatives. In this chapter, we will study the applications of the derivatives in various disciplines in engineering, science, social science, and many other fields. We will also learn how the derivative can be used. 1. To determine the rate of change of quantities. 2. To find the equations of tangent and normal to a curve at a point. 3. To find turning points on the graph of a function, which in turn will help us to locate points at which the largest or the smallest value of a function occurs. We will also use derivatives to find intervals on which a function is increasing or decreasing, and finally we use the derivative to find approximate values of certain quantities. Rate of change of quantities. Recall that by derivative ds by dt, we mean the rate of change of distance s with respect to the time t. In a similar fashion, whenever one quantity y varies with another quantity x, satisfying some rule y is equal to f of x, then dy by dx or f dash of x represents the rate of change of y with respect to x, and dy by dx x is equal to x naught or f dash of x naught represents the rate of change of y with respect to x at x is equal to x naught.
Application of derivatives. Further, if two variables x and y varying with respect to another variable t, that is, if x equal to f of t and y equal to g of t, then by chain rule dy by dx equal to dy by dt by dx by dt if dx by dt is not equal to 0. Thus, the rate of change of y with respect to x can be calculated using the rate of change of y and that of x both with respect to t.
Increasing and decreasing function. In this section, we will use differentiation to find out whether a function is increasing or decreasing or none. Consider the function f given by f of x is equal to x squared, x belongs to R. The graph of this function is a parabola as given in the figure.
First, consider the graph to the right of the origin. Observe that as we move from left to right along the graph, the height of the graph continuously increases. For this reason, the function is said to be increasing for the real number x greater than 0. Now, consider the graph to the left of the origin and observe here that as we move from the left to right along the graph, the height of the graph continuously decreases. Consequently, the function is said to be decreasing for the real numbers x lesser than 0. We shall now give the following analytical definitions for a function which is increasing or decreasing on an interval.
Definition 1. Let I be an open interval contained in the domain of a real valued function f. Then f is said to be as shown. Definition 2. Let x0 be a point in the domain of definition of a real valued function f. Then f is said to be increasing, strictly increasing, decreasing or strictly decreasing at x0 if there exists an open interval I containing x0 such that f is increasing, strictly increasing, decreasing or strictly decreasing respectively in I. Let us clarify this definition for the case of increasing function as shown. Show that the function given by f of x is equal to 7x minus 3 is strictly increasing on R. Solution. Let x1 and x2 be any two numbers in R. Then x1 is lesser than x2 implies 7x1 is lesser than 7x2 implies 7x1 minus 3 is lesser than 7x2 minus 3, which implies f of x1 is lesser than f of x2. Thus, by definition 1, it follows that f is strictly increasing on R. Theorem 1. Let f be continuous on a comma b and differentiable on the open interval a comma b. Then f is increasing in a comma b if f dash of x is greater than 0 for each x belongs to a comma b. F is decreasing in a comma b if f dash of x is lesser than 0 for each x belongs to a comma b. F is a constant function in a comma b if f dash of x is equal to 0 for each x belongs to a comma b. Proof. The proof is shown on the screen.
Remarks. First, f is strictly increasing in AB if f dash x lesser than 0 for each x belongs to AB. Second, f is strictly decreasing in AB if f dash x lesser than 0 for each x belongs to AB. Third, a function will be increasing or decreasing in R if it is so in every interval of R.
Prove that the function given by f of x is equal to cos x is strictly decreasing in 0, pi, strictly increasing in pi, 2 pi, and neither increasing nor decreasing in 0, 2 pi. Solution. Note that f dash of x is equal to minus sin x. Since for each x belongs to 0, pi, sin x is greater than 0, we have f dash of x lesser than 0 and so f is strictly decreasing in 0, pi. B. Since for each x belongs to pi, 2 pi, sin x is lesser than 0, we have f dash of x greater than 0 and so f is strictly increasing in pi, 2 pi. C. Clearly, by A and B above, f is neither increasing nor decreasing in 0, 2 pi.
Tangents and normals. In this section, we shall use differentiation to find the equation of the tangent line and the normal line to a curve at a given point. Recall that the equation of a straight line passing through a given point x0, y0 having finite slope m is given by y minus y0 is equal to m into x minus x0 the whole.
Note that the slope of the tangent to the curve y equal to f of x at the point x0, y0 is given dy by dx x0, y0 to the curve y equal to f of x is given by y minus y0 equal to f dash x0 into x minus x0. Also, since the normal is perpendicular to the tangent, the slope of the normal to the curve y equal to f of x at x0, y0 is minus 1 by f dash x0 if f dash x0 is not equal to 0. Therefore, the equation of the normal to the curve y equal to f of x at x0, y0 is given by y minus y0 equal to minus 1 by f dash x0 into x minus x0, that is y minus y0 into f dash x0 plus x minus x0 equal to 0. Particular cases. First, if slope of the tangent line is 0, then tan theta equal to 0 and so theta equal to 0, which means the tangent line is parallel to the x-axis. In this case, the equation of the tangent at the point x0, y0 is given by y equal to y0. Second, if theta implies pi by 2, then tan theta implies infinity, which means the tangent line is perpendicular to the x-axis, that is, parallel to the y-axis. In this case, the equation of the tangent at x0, y0 is given by x equal to x0.
Find the point at which the tangent to the curve y root of 4x minus 3 minus 1 has its slope 2 by 3. Solution. Slope of tangent to the given curve at x comma y is dy by dx is equal to 1 by 2 into 4x minus 3 to the whole power minus 1 by 2 into 4 is equal to 2 by the square root of 4x minus 3. The slope is given to be 2 by 3. So, 2 by the root of 4x minus 3 is equal to 2 by 3, or 4x minus 3 is equal to 9, or x is equal to 3. Now, y is equal to the root of 4x minus 3 minus 1. So, when x is equal to 3, y is equal to the root of 4 into 3 minus 3 minus 1 is equal to 2. Therefore, the required point is 3, 2.
Example. Find the equation of the tangent to the curve y equal to x minus 7 by x minus 2 into x minus 3 at the point where it cuts the x-axis. Solution. Note that on x-axis y equal to 0. So, the equation of the curve when y equal to 0 gives x equal to 7. Thus, the curve cuts the x-axis at 7, 0. Now, differentiating the equation of the curve with respect to x, we obtain dy by dx equal to 1 minus y into 2x minus 5 by x minus 2 into x minus 3, or dy by dx 7, 0 equal to 1 minus 0 by 5 into 4 equal to 1 by 20. Therefore, the slope of the tangent at 7, 0 is 1 by 20. Hence, the equation of the tangent at 7, 0 is y minus 0 equal to 1 by 20 into x minus 7, or 20y minus x plus 7 equal to 0.
Approximation. In this section, we will use differentials to approximate values of certain quantities. Let f from d to r, d subset of r, be a given function, and let y is equal to f of x. Let delta x denote a small increment in x. Recall that the increment in y corresponding to the increment in x denoted by delta y is given by delta y is equal to f of x plus delta x minus f of x. We define the following. 1. The differential of x denoted by dx is defined by dx is equal to delta x. 2. The differential of y denoted by dy is defined by dy is equal to f of x dx, or dy is equal to dy by dx into delta x.
Use differential to approximate 25 to the power 1 by 3. Solution. Let y is equal to x to the power 1 by 3. Let x is equal to 27, and let delta x is equal to minus 2. Then delta y is equal to x plus delta x to the whole power 1 by 3 minus x to the power 1 by 3 is equal to 25 to the power 1 by 3 minus 27 to the power 1 by 3 is equal to 25 to the power 1 by 3 minus 3, or 25 to the power 1 by 3 is equal to 3 plus delta y. Now, dy is approximately equal to delta y and is given by dy is equal to dy by dx into delta x is equal to 1 by 3x to the power 2 by 3 into minus 2, as y is equal to x power 1 by 3 is equal to 1 by 3 into 27 power 1 by 3 square into minus 2 is equal to minus 2 by 27 is equal to minus 0.074. Thus, the approximate value of 25 power 1 by 3 is given by 3 plus minus 0.074 is equal to 2.926.
Maxima and minima. In this section, we will use the concept of derivatives to calculate the maximum or minimum values of various functions. Further, we will also find the absolute maximum and absolute minimum of a function that are necessary for the solution of many applied problems.
Let us consider the following problems that arise in day-to-day life. The profit from a grove of orange trees is given by P of x is equal to ax plus bx square, where a and b are constants and x is the number of orange trees per acre. How many trees per acre will maximize the profit? A ball thrown into the air from a building 60 meters high travels along a path given by h of x is equal to 60 plus x minus x square by 60, where x is the horizontal distance from the building and h of x is the height of the ball. What is the maximum height the ball will reach? An opaque helicopter of enemy is flying along the path given by the curve f of x is equal to x square plus 7. A soldier placed at a point 1, 2 wants to shoot the helicopter when it is nearest to him. What is the nearest distance? In each of the above problem, there is something common. That is, we wish to find out the maximum or minimum values of the given functions. In order to tackle such problems, we first formally define maximum of minimum values of a function, points of local maxima and minima, and test for determining such points. Definition 3. Let f be a function defined on the interval I. Then f is said to have a maximum value in I if there exists a point C in I such that f of C is greater than f of x for all x belongs to I. Find the maximum and the minimum values if any of the function f given by f of x is equal to x square, where x belongs to R. Solution. From the graph of the given function, we have f of x is equal to 0 if x is equal to 0. Also, f of x is greater than or equal to 0 for all x belongs to R. Therefore, the minimum value of f is 0 and the point of minimum value of f is x is equal to 0. Further, it may be observed from the graph of the function that f has no maximum value and hence no point of maximum value of f in R.
Find the maximum and minimum values of f if any of the function given by f of x equal to mod x, x belongs to R. Solution. From the graph of the given function, note that f of x greater than or equal to 0 for all x belongs to R and f of x equal to 0 if x equal to 0. Therefore, the function f has a minimum value 0 and the point of minimum value of f is x equal to 0. Also, the graph clearly shows that f has no maximum value in the R and hence no point of maximum value in R.
The local maximum value and the local minimum value. Let us now examine the graph of a function as shown in the figure. Observe that at points A, B, C and D on the graph, the function changes its nature from decreasing to increasing or vice versa. These points may be called turning points of the given function. Further, observe that at turning points, the graph has either a little hill or a little valley. Roughly speaking, the function has minimum value in some neighborhood interval of each of the points A and C which are at the bottom of their respective valleys. Similarly, the function has maximum value in some neighborhood of points B and D which are at the top of their respective hills. For this reason, the points A and C may be regarded as points of local minimum value or relative minimum value, and points B and D may be regarded as points of local maximum value or relative maximum value for the function. The local maximum value and the local minimum value of the function are referred to as local maxima and local minima respectively of the function. We now formally given the following definition. Definition 4. Let f be a real valued function and let C be an interior point in the domain of f. Then the following values are arrived as shown.
Geometrically, the above definition states that if x equal to c is the point of local maxima of f, then the graph of f around c will be shown in figure. Note that the function f is increasing, that is, f dash x greater than 0 in the interval c minus h, c, and decreasing, that is, f dash x lesser than 0 in the interval c, c plus h. This suggests that f dash c must be 0. Similarly, if c is a point of local minima of f, then the graph of f around c will be as shown in the figure. Here, f is decreasing, that is, f dash x 0 in the interval c minus h, c, and increasing, that is, f dash x is greater than 0 in the interval c, c plus h. This again suggests that f dash c must be 0.
First derivative test. Let f be a function defined on an open interval I. Let f be continuous at the critical point c in I. Then the following values are arrived as given. Find all points of local maxima and local minima of the function f given by f of x is equal to x cube minus 3x plus 3. Solution. We have f of x is equal to x cube minus 3x plus 3, or f dash of x is equal to 3x square minus 3 is equal to 3 into x minus 1 into x plus 1, or f dash of x is equal to 0 at x is equal to 1 and x is equal to minus 1. Thus, x is equal to plus or minus 1 are the only critical points which could possibly be the points of local maxima or local minima of f. Let us first examine the point x is equal to 1. Note that for the values close to 1 and to the right of 1, f dash of x is greater than 0, and for values close to 1 and to the left of 1, f dash of x is lesser than 0. Therefore, by first derivative test, x is equal to 1 is the point of local minima and local minimum value is f of 1 is equal to 1. In the case of x is equal to minus 1, note that f dash of x is greater than 0 for values close to and to the left of minus 1, and f dash of x is lesser than 0 for values close to and to the right of minus 1. Therefore, by first derivative test, x is equal to minus 1 is a point of local maxima and local maximum value is f of minus 1 is equal to 5. Second derivative test. Let f be a function defined on an interval I and c belongs to I. Let f be twice differentiable at c. Then the following values are arrived as shown. Find local minimum value of the function f given by f of x is equal to 3 plus modulus of x where x belongs to R. Solution. Note that the given function is not differentiable at x is equal to 0. So, second derivative test fails. Let us try first derivative test. Note that 0 is a critical point of f. Now, to the left of 0, f of x is equal to 3 minus x, and so f dash of x is equal to minus 1 lesser than 0. Also, to the right of 0, f of x is equal to 3 plus x, and so f dash of x is equal to 1 greater than 0. Therefore, by first derivative test, x is equal to 0 is point of local minima of f and local minimum value of f is f of 0 is equal to 3.
Example, find all the points of local maxima and local minima of the function f given by f of x equal to 2x cube minus 6x square plus 6x plus 5. Solution, we have f of x equal to 2x cube minus 6x square plus 6x plus 5 or f dash x equal to 6x square minus 12x plus 6 equal to 6 into x minus 1 whole square. F dash x equal to 12 into x minus 1. Now, f dash x equal to 0 gives x equal to 1. Also, f dash 1 equal to 0. Therefore, the second derivative test fails in this case. So, we shall go back to the first derivative test. We have already seen that using first derivative test x equal to 1 is neither a point of local maxima nor a point of local minima, and so it is a point of inflection.
Maximum and minimum values of a function in a closed interval. Let us consider a function f given by f of x is equal to x plus 2, x belongs to 0, 1. Observe that the function is continuous on 0, 1 and neither has a maximum value nor has a minimum value. Further, we may note that the function even has neither a local maximum value nor a local minimum value.
Maximum and minimum values of a function in a closed interval. However, if we extend the domain of f to the closed interval 0, 1, the f still may not have a local maximum or minimum values, but it certainly does have maximum value 3 equal to f1 and minimum value 2 equal to f of 0. The maximum value 3 of f at x equal to 1 is called absolute maximum value or greatest value of f on the interval 0, 1. Similarly, the minimum value of 2 of f at x equal to 0 is called the absolute minimum value or least value of f on 0, 1.
Example, consider the graph given in figure of a continuous function defined on a closed interval a, b. Observe that the function f has a local minima at x is equal to b and local minimum value is f of b. The function also has a local maxima at x is equal to c and local maximum value is f of c. Also, from the graph, it is evident that f has absolute maximum value f of a and absolute minimum value f of d. Further, note that the absolute maximum minimum value of f is different from local maximum minimum value of f. Theorem 5. Let f be a continuous function on an interval I is equal to a, b. Then f has the absolute maximum value and f attains it at least once in I. Also, f has the absolute minimum value and attains it at least once in I. Theorem 6. Let f be a differentiable function on a closed interval I and let c be an interior point of I. Then f dash of c is equal to 0 if f attains its absolute maximum value at c. F dash of c is equal to 0 if f attains its absolute minimum value at c. In view of the above results, we have the following working rule for finding absolute maximum and or absolute minimum values of a function in a given closed interval a, b.
Working rule. Step 1. Find all critical points of f in the interval, that is, find points x where either f dash x equal to 0 or f is not differentiable. Step 2. Take the endpoints of the interval. Step 3. At all these points listed in step 1 and step 2, calculate the values of f. Step 4. Identify the maximum and minimum values of f out of the values calculated in. Step 3. This maximum value will be absolute maximum greatest value of f and the minimum value will be absolute minimum least value of f. Example, a man of height 2 meters walks at a uniform speed of 5 km high away from a lamp post which is 6 meters high. Find the rate at which the length of his shadow increases. Solution. In figure, let AB be the lamp post, the lamp being at the position B, and let MN be the man at a particular time t, and let AM equal to 1 meters. Then MS is the shadow of the man. Let MS equal to S meters. Note that triangle MSN is similar to triangle ASB, or MS by AS equal to MN by AB, or AS equal to 3S, ASMN equal to 2, and AB equal to 6 given. Thus, AM equal to 3S minus S equal to 2S, but MA equal to 1. So, L equal to 2S. Therefore, dL by dt equal to 2 ds by dt. Since dL by dt equal to 5 km, hence, the length of the shadow increases at the rate 5 by 2 km high.